Okay, so now that we've talked about what exactly the base dissociation constant Kb is, now we're going to look at how do we solve for Kb. And this is going to be very similar to what we just did with solving for Ka. So the first step we're always going to do is going to be to write the base dissociation constant equation. That's going to be what we usually do to start all of our steps. Pretty much if you're when in doubt, write down the equilibrium constant equation. Okay, the next step is going to be to make an ice table. Okay, remember what that is. Ice is initial change equilibrium. Okay, then we're going to plug in all values into the ice table. Then we're going to determine the equilibrium concentration of our hydroxide ion from the pOH, if that's given. If we're given the pH, which will be probably more common, you're going to calculate to find the pOH. Okay? 5 is going to be to find the change in concentration for each product and reactant. Then you're going to use these equilibrium concentrations to find Kb. Okay, so let's look at what we're going to do here for this first question here. Okay, so when a 0.15 solution of ammonia, which that is a base, is prepared, the pOH is found to be 2.80 at 25 degrees C. Now remember, we have pOH here, so that should be accurate to have a 2.80 pOH, because the pH would probably be about 12, which is about accurate. Okay? The base dissociation, what is the base dissociation constant Kb? Okay? So first thing I'm going to do is write my base dissociation equation. I'm not concerned with my water because remember that is a liquid. So all I'm going to write is going to be my ammonium ion and my hydroxide ion all over my ammonia concentration. Okay, so remember, products over reactants. Now I'm going to write into my ice table. So I have started off with a 0.15 molar solution, and then both of these again would be 0 because this is before we've done any dissociation. Okay? Then we're going to go, if we add any concentration over here on the left, where equilibrium will move to the right towards the products. So we're going to subtract out x, add x, and add x. Okay? So I'm not going to write in my equilibrium concentrations just yet because I can solve using my pOH for my equilibrium concentration of my hydroxide ion. So I'm going to do that. Okay. So remember, we're going to go ahead and plug in our pOH And we're going to solve similar to how we solve for our pH. So when we substitute everything in, our hydroxide concentration should be 10 to the negative 2.80. So we go ahead and put that into our calculator.
So we try and do it once a year.
So, and we're going to round off to 3 decimal places right there. Okay? Okay. So now we're going to determine the equilibrium concentration for our ammonia. So that's going to be 0.15. Let's put everything back in first into our equation, or into our ice table. Okay, remember this is going to be our x value because that's how much we've changed. We started at 0, we added x, and we've gotten here. So that must be our x value. Okay, so then we're going to solve for our ammonia concentration. So if I put that into my calculator, I'm going to get this, which that is pretty much rounded off to the same number of 0.15. So I go ahead and put that back in for my base dissociation constant equation.
No other former president is putting their 2 cents in. Typically when a president leaves office, they sit back and just live the rest of their life.
Exactly, and I don't think that he involved.
I'm sorry, he's already said this.
So we put in our concentrations for our ammonia and for our hydroxide. And then we're going to put that over our ammonium ion and our hydroxide ion. We're going to put in our ammonia concentration. So going ahead and putting that in there. And we're going to put that into our calculator. Okay. So that's going to round off to 1.7 times 10 to the negative 5th. Okay, so if that's what you got for your answer, you're doing it correctly. Okay. So that's how we would find Kb. Now, why am I going to go through this whole situation of finding Kb and Ka? Okay. Well, essentially, right, we can relate Kb and Ka through POH and pH. So there's a way we can probably relate them together because we can relate pH and POH. So, looking at this equation here, this is an equation for what would be a buffer solution. You have an ammonia, an ammonium, acid, and base. Okay, so this is going to be an acid-base similar equation. If we write the acid form of this equation and write about the Ka, this is what we would get. Okay, now if we write the Kb, this is what we'll get. Something similar to what we just saw in our last equation. Okay, so now what I can do is, if this is the acid portion, this is the base portion of that equation, I can combine these equations to get to some neutral equation. Okay, does this make sense for everybody? So that's what we're going to do right here, right now. So we're going to take my acid form of the equation. And we're going to take our base form of the equation. Okay? So when I combine those, I can take, essentially just like we were eliminating when we were doing spectator ions, I'm going to do the same thing over here. So I'm going to eliminate anything that's the same on both sides of the equation. So this is going to be the same, and this is the same. So therefore, I'm going to be left with H2O is going to go to form H plus and OH minus 1. Okay? So this is going to have what we call KW. Okay? And that's because it's a KW of water. It's going to equal something like this. So, remember we started out here, we have Ka and Kb. So when we combine these, remember what did we do? We multiplied them together from the last, remember, from the last one? So if I do that, I take Ka times Kb, that'll equal
We'll change. No screaming, cause Mom's sleeping. Can't scream. I heard the baby in the background.
They've already heard the baby in the background. FYI, my daughter's about to be changed, so if you hear screaming, ignore it. Okay, so now we're going to go ahead and eliminate things that we can eliminate. Just like thinking of this as one whole, fraction. So I can eliminate this and this. So when I get Ka times Kb, that goes to form H plus 1 times OH minus 1. That's the same thing as Kw, so we can figure out that Kw is equal to Ka times Kb. And you're going to learn that Kw is equal to 1.0 times 10 to the negative 14. And if you take the log, negative log of that, you're going to find that that equals 14. So therefore, we're stating that this is going to be able to make us at equilibrium. This is the pH, this is the pOH, okay? And when we multiply those together, or when we add them together, essentially we're going to get Kw. Okay? So that's how we can relate Kb and Ka. Now the next thing we're going to talk about is going to be conjugate acid and base pairs. Okay, and this is kind of important, especially in our next concept, which we're going to talk about, which will be buffers. Okay, so conjugate acid. Okay, so that's the first thing we're going to talk about. This is formed by adding a proton to a base in an acid-base reaction. Okay, so it's always going to be a base that'll have a conjugate acid. Okay, some things to know. If you have a strong base, you'll have a weak conjugate acid. If you have a weak base, you're going to have a strong conjugate acid. Okay, now if we're looking at a conjugate base, well, if we added a proton to a base here, and we have a base to conjugate acid, okay, a conjugate base this is going to be formed by removing a proton from an acid base reaction. We have a strong acid, again, what do you think? We're going to have a weak conjugate base. And if we have a weak acid, we're going to have a strong conjugate base. Remember here, again, if you have an acid, you're going to have a conjugate base. Okay, so if we look here, we've got an acid, and we're removing a proton or a hydrogen plus one ion. So therefore, we're going to have a conjugate base. Okay, here, we're going to be adding an H plus 1 ion. So this is going to be a base. This is our base here. And now we have a conjugate acid. Now water could act as a base or an acid, but because we have an acid to start here, we're going to have water acting as a base. Okay. So why does it matter to know about conjugate acids and conjugate bases? Well, that's where we get into this thing called buffers. And this is what you're mostly going to be concerned with because you probably have dealt with buffers at some point, whether it's, something you've had to put into a dog, or when you're talking about your stomach acid. That is actually technically a buffer, okay? And that's going to be a weak acid or a weak base. Okay, so it could be either one of those. And then you're going to have the salt of the acid or base. This will essentially just be your conjugate acid or base, depending on what you have. Okay? When you have those together, you get a buffer. Okay, here, so this is an example here. We've got, this would be our conjugate this would be our base, and this is our conjugate acid. Okay, I almost misspoke there. So what happens here? This is going to be essentially if you add any type of base to your buffer, okay? So the presence of our conjugate acid or our acid counteracts the addition of OH minus 1. So the most you're going to see here is going to be a small increase in pH. Here, if you add some type of acidic substance here, the presence of our A minus 1, which is also our conjugate or base or our base, this will counteract the addition of that H plus or that acidic substance, and you're going to see only a small decrease in pH. Okay? So, if we're calculating the pH of a buffer, okay, this is actually pretty easy.
I'm waiting for my mom to call back.
Okay?
She's back into the garage.
So, the first thing you're going to do is you're going to calculate the pKa of the acid using the following equation. Okay? So, now remember we talked about this earlier. The change that we're going to see is going to be negligible because of in our acid and bases, because the hydrogen ion concentration or the hydroxide ion concentration is going to be very low. So therefore, we can assume, because our change is small, we're just going to use the initial concentrations of the acid and base in the Henderson-Hasselbalch equation. And you got to make sure you have that pKa. So with the pKa to find your pH. Okay, so we're going to round to 2 decimal places. Okay, so that's how we're going to calculate the pH of a buffer. So, first thing, this is going to be pretty easy for us. We have our Ka. Okay, what is the pH of a buffer that is 0.12 molar lactic acid and 0.10 sodium lactate? So the idea here is that our conjugate base is this, and it's shown in our equation right here. So the first thing we're going to do is we're going to find our pKa. So it's going to be the negative log of our Ka. So our pKa is going to equal the negative log of 1.4 times 10 to the negative 4th. Put that into your calculator. Okay, we're going to round to 2 decimal places. So 3.85. Now the next one is to find the pH. So we're going to use our Henderson-Hasselbalch equation. So the pH is equal to the pKa plus the log of the concentration of the base over the acid. Okay, so this is our base here. And obviously this is going to be our acid. Okay, so we're going to have our pKa plus the log of our base, so 0.10, all over 0.12. Okay, so we put that into our calculator. Okay, and this is what we get. We're going to round to 2 decimal places, so 3.77. And that's pretty easy, and all is really necessary to do for this equation. Let's go ahead, we'll talk about buffer capacity in the next video.